So now we continue with the propagation of sound, and we are going to see that how the propagation of sound takes place in a medium. When a source of sound vibrates, it creates a periodic disturbance in the medium near it. So when something vibrates, there is going to be a periodic kind of disturbance in the medium around it. The state of particles of medium changes. The disturbance then travels in the medium in the form of waves. This can be understood by the following experiment. So what we are going to do is we are having a small experiment in which we are going to see that how a metallic strip, so if I take this metallic strip, now if this starts vibrating, so what has happened, it is going from the mean position, it goes to the left over here and then goes to the right over here and left right ऐसे करके जा रहा है. So this point से इधर जब भी जा रहा है तो it is pressing the particles also. So let's see if the propagation sound is in this direction, then what is going to happen to the particles which are here, so in this particular kind of experiment. So what we see is, let's see the first kind of condition. The first condition is you're having the metallic strip to be something like this, and the the material medium is going to be in a normal condition, that they will be neither be compressed nor they are going to be stretched, and the particles will be just going to be like this. So they are going to be in a uniform pattern, so uniform distance पे the particles of the medium are here. Now when I put it this way, so ऐसा press किया, the moment I press it this way, so this thing is coming up in a form like this. Okay, I pushed it like this, so I took it and pressed it like this. So जैसे इसको press किया, तो क्या होगा? When it is pressed, it is going to give a effect on the near particles, and they are going to get compressed. So because of this, the near particles are going to get compressed, and that's why they are going to come very close to each other. Okay, and then the rest of the particle is not going to be affected, but it is going to be just remaining same. So that's why the rest of the particles will be just like this. कि इसके नीचे ये सब same रहेगा. Now, so this is the first condition, wherein due to the movement of the metallic strip on one side, the particles over there has got pressed. So if यह particle था, ये इधर दब गया, तो ये थोड़ा push होगा when they are getting condensed. So this condensation over here is called as compression. So this is called, this much part over here is called as compression, denoted as C. Now the next thing what happens is your scale becomes flat again. So it is going to become, पहले इधर गया और वापस सीधा हो गया, तो अभी वापस सीधा हुआ. तो as soon as it becomes back to like this, now what has happened? Because it has come this way, so the particles will relax a bit, but by the time this was already pushed forward, so this one has already pushed. It is something like there are multiple cycles which are standing over here, और एक cycle को धक्का मार तो क्या होता है, एक cycle ने दूसरे को गिरा, फिर तीसरे को गिरा, ऐसे करके गिरते जाएगा. But remember, over here, because the cycles are not in a way that they are going to come back to its original position, that means they are not elastic in nature, that's why they are just going to remain fall down. तो ये सब गिरे हुए रहेंगे. तो यहाँ पे भी वही होगा कि ये दब गया, बट अभी वो दबा हुआ part is going to move forward because it is just going to press the next particle, then the next particle, then the next particle. But the original particle, because it is elastic in nature, it comes back to its normal state. Hence, what is seen is there will be the normal kind of a wave for the first two, and then this compression has moved a bit and it has reached this particular place. So this compression is now reached here. So this thing has now reached over here because it will be propagating further. बाकी का part जो है वो same ही रहेगा. So that will be the same way they're coming over here in this pattern. So you can see that this compression has moved forward. It has been moved The particles are not moved. The particle has transmitted the force from one to another. यानी एक साइकिल ने को हम लोग ने गिराया, वो साइकिल ने दूसरे को गिराया, उसने तीसरे को गिराया, इसने चौथे को गिराया. ऐसे करके all the cycles are falling down. So this is what exactly happening is there's a push over here. The next condition will be again it is going to go now. We know that the strip is going to go from here, it's going to come here and then go back. Okay, it is going to be like this. It is going to be moving this way. So when it comes back over here, at that time there will be something like a suction. Okay, there will be something like a suction which is going to take place. So this is going to be in this form. Okay, due to this, there is going to be the particles will be attracted because there will be something a kind of a low pressure created here, due to which the particle will be attracted towards this, and hence the particles is going to spread out. So you will be one over here, the next over here, the third over here, then you will be having a few ones over here, and then you will be having this thing coming up here. So this will be your C. And this part over here is your rarefaction. That is nothing but the expansion, or you can say stretching of the particles from each other. The material, because it is going to have a low pressure generated, because it has gone this way, so it has sucked some air particles or the medium particles, and that's why there is some kind of a rarefaction being formed over here. And then again it is going to come back to its original position. When it is done, this is moved forward, and okay, so this is just normal. And hence when it comes to normal, यहाँ पे इधर पहले दो normal हो गए, then there is a rarefaction part. So there will be the rarefaction which is a part, and then some part, and then it will be the just missed out over here, and then there will be this kind of a compression. So this is going to be the rarefaction, this is the compression. So you can see that the rarefaction and compression are alternate. Rarefaction compression is going to move from material medium from one point to another point. So this way it is very much clearly given in the textbook also, where the movement of the rarefaction and the compression is given properly from यहाँ से फिर यहाँ पे फिर यहाँ पे फिर यहाँ पे ऐसे करके figure 8.5 में दिया है. So this is exactly what I am trying to say here, that they are moving in a direction in this way, so that the completeness, this rarefaction and compression का जो ये part है, it is traveling in the medium. So that is what they explained here. So let's go through that thing. Take a thin strip, metal strip, keeping it vertical, fix its lower end, push its upper end to one side and then release it. As it vibrates, that is moves alternate to left and right, sound is heard. Figure 8.5 shows the undisturbed or normal A shows undisturbed normal position of the metal strip, and the air layers on the right side near the strip in their undisturbed or normal position. As the strip moves to the right from A to B, that is in figure 8.5b, it pushes the particles of the air in a layer in front of it. So the particles of the air in this layer get closer to each other. That is, air of these layers get compressed, or compression is formed at C. The particles of this layer, while moving towards right, pushes and compresses the layer next to them, which then compresses the next layer, and so on. Thus the disturbance moves forward in form of compressions. The particles of the medium get displaced, but they do not move away along with the compression. So you can see that this compression is going to move from this compression. The particles are not moving, but the particles is pushing the next one, then it pushes the next one, then it pushes the next one. ऐसे करके the compression is moving in the material medium. When the strip moves to the left from A to C, that is in figure 8.5d, it pushes back the layers of air near it towards its left and thus produces a space of very low pressure on its sides. The air layer on the right side of the strip expands in this region, thus forming the rarefied air layers. This region of low pressure is called as rarefaction R. So this is the low pressure rarefaction R, which is going to be absorbed. You know, they are going to get sucking action जैसा होगा for this part. When the strip returns to C at its normal position A, it pushes the rarefaction forward and the air layer near the strip again passes through their mean position due to the elasticity of the medium. So due to the elasticity of the medium, it is going to come back to normal, whereas the complete set of rarefaction and compression is pushed forward by the strip coming back to normal. In this manner, as strip moves to the right and left repeatedly, the compression and rarefaction regions are produced one after the other, and which carry the disturbance with it with a definite speed depending on the nature of the medium. Gradually, due to friction, the strip loses its energy and the medium to the medium, and disturbance dies out. So that is what we are saying, that if I start this in vibration, you can see immediately after some time it got stopped because of the vibrations or because of the friction in the air, due to which it stopped vibrating. So you can see the vibration was there only for a certain period and then it is stopping over there, because एक तो सबसे पहले ये बहुत firmly पकड़ा, इसलिए अगर मैं loosely पकड़ूंगा तो गिर जाएगा. That's why I need to keep it firm, but it is going to go for a lesser time. So this is how the longitudinal waves are going to be formed. So one complete to and fro motion of the strip forms one compression and one rarefaction. So one complete to and fro, यानी यहाँ से इधर, back इधर and back इधर. Yeah, this is one complete oscillation. Okay. From center to one end, again center, another end, again center. This is one complete vibration. This complete vibration produces one compression and one rarefaction. Okay, when one particular vibration of the strip is going to produce one compression and one rarefaction, which together constitute to one wave. So what is one wave in case of a longitudinal wave? What is one wave? One wave is one compression with one rarefaction. This wave in which the particles of medium vibrate above their mean position in the direction of propagation of sound is called as longitudinal wave. So when the wave is such that the vibration of the medium particle is in the direction of the transmission of the wave or direction of the propagation of the sound, it is called as longitudinal wave. So this particular kind of wave is called as longitudinal wave. Okay, this is longitudinal wave. Thus, sound waves in air in the form of longitudinal waves. So sound waves in the air are longitudinal waves. Actually, the longitudinal waves can be produced in solids and liquid as well as in gases. At compression, the density and pressure of the medium is maximum, while at rarefaction the density and pressure of the medium is minimum. So obviously, because there will be a compression rarefaction over here, so during the compression यहाँ पे density अपने आप बढ़ गया because the number of particles over there are more, and in rarefaction the density अपने आप घट गया because the number of particles are less. So during the longitudinal waves, wherever there is a compression taking place, the density of the medium increases, whereas wherever there is the rarefaction, there the density of the medium decreases. So this is how the waves are going to travel inside solids, liquids, or of course gases. So that is how the sound wave travels inside the medium. Now we see the next part, that is how the wave travels on the surface of a medium. So I'll just erase this much part. Now whenever it is on the surface of a medium, we can easily compare it to the surface of water. Suppose we take a steady water. We can just a steady water is there. Suppose there is a lake, which is water is not even having any ripples at all. और वो steady water में अगर हमने एक stone फेंका, तो क्या होगा? You will find where it dips, there is going to be ripples formed on all sides. And suppose at that particular point, if I take a cork sheet, which is anything which is floating, I take some floating body which I placed it on the water, and then I put the ripples on. What will happen? The originally it was like this, and the body was over here, that floating body. As soon as the ripples are there, the ripples are going to form like this. So accordingly with this, the body also goes up and down over here. So the body is going to move up and down over here with the waves. So this exactly is how the waves are going to travel, of sound travel on the surface of the solid or liquid. So let's see. In the above example, formation of wave in the air could not be seen. The formation of wave can easily be seen on the surface of water. If we drop a piece of stone in the still water of a pond, we hear the sound of the stone striking the water surface. Actually, a disturbance is produced in water at the point where the stone strikes it. This disturbance spreads in all directions radially outwards in forms of circular waves or ripples on the surface of water as shown in the figure. So as soon as I hit it, there will be ripples on all sides, all around the circular part. There will be the ripples which are going to be formed. Now if we take a piece of cork on the water surface at some distance away from the point where the stone strikes the water, we notice that the cork does not move ahead, but it moves up and down while the wave moves ahead. So when the wave moves ahead, this cork sheet is just going to go up and down. It is not, the cork वो है क्या होगा, ऊपर जाके नीचे जाएगा, ऊपर जाके नीचे जाएगा, ये इधर रहेगा, but the waves are just moving. So wave नीचे गया तो ये नीचे गया, ये ऊपर गया नीचे, wave आगे पास होगा तो दूसरा एक wave आके उसको ऊपर नीचे करेगा. So the particle does not move. Okay, the particle over here, the cork does not move. So you can see that we notice that the cork does not move ahead, but it moves up and down while the wave moves ahead. The reason is that the particles of the water or medium starts vibrating up and down, and at the point where the stone strikes. These particles then transfer their energy to the neighboring particle, and they themselves come back to their main position. So what happens is, on the formation of ripples, तो ये जो पार्ट है इससे धक्का मार के नेक्स्ट वाले को धक्का मारा फिर आएगा, पर ये खुद क्या हो गया, it became normal. So that's why the ripple keeps on dampening. Okay, पहले इतना वेव रहेगा तो धीरे धीरे छोटा छोटा होते it becomes steady. So you can see that particular formation of the ripples will be there, wherein the particles are allowing the neighboring particle to start vibrating, and khud comes to, I mean, that particular own item, that particular material or the particle comes back to its original position. This process continues, and thus the disturbance moves ahead on the water surface in the form of waves as shown in figure 8.7. The wave die out as soon as the energy imparted by the stone gets dissipated. However, it is possible to obtain a continuous traveling wave if a periodic disturbance is produced at the point of striking the stone on the water surface. So if you are able to periodically give it a particular some kind of a disturbance, then the ripples will keep on going. Like for example, if you take a glass, और glass में पानी भरा हुआ है, and you put it underneath a tap which is leaking, so what will happen, after every 1 second or 2 seconds that there is going to be a droplet of water coming in. So due to that, there will be a continuous ripple which will be formed on the surface of the glass, because वो गिरेगा ripple बनाएगा, next year ripple बनाएगा, next year ripple. So by the time it could dissipate the energy which is given by the first drop, the next drop is already available. So that's why we do a periodic disturbance given to that particular steady water. There will be continuous ripples which will be formed on the surface of the water. The wave in which the particle medium vibrates above their mean position in a direction perpendicular to the direction of propagation of the wave is called as transverse wave. So this over here, what is happening is the movement is like this. These are the waves, and the particle is going to move from here to upwards and then downwards. ऐसे करें particle तो इसे wave के आगे पीछे जाने के कारण it is just going to move up and down. So the particle is not going to go anywhere. It is just going to be so the movement of the particle is not in the direction of the flow of the sound, but it is perpendicular to it. Such a kind of the movement or such a kind of a wave is called as transverse wave. So longitudinal wave is the wave in which the particles move in the direction of the propagation of sound, whereas here it is perpendicular direction of the propagation of sound. A transverse wave is composed of a crest and trough. So this over here is a crest, this is the crest. जैसे यहाँ पे compression rarefaction था, वैसे यहाँ पे crest है और ये है trough. So crest and trough are the up and down movements of the waves. Upwards crest, downwards trough. The position of maximum upward displacement is called as the crest, while the position of the maximum downward displacement is called as the trough. The transverse waves can only be produced in solids or in surface of liquids. They cannot be produced inside liquid or inside the gases. Okay, ये surface पे होता है. Because it is only on the surface, so it can be there only on solids, on the surface of solids or on the surface of liquids. Because gases do not have any surface, they cannot be produced in gases. So that's why this one over here can be in gas, liquid and solid, where this one will be only in surface of liquids and solids. Okay, so that's the difference between the longitudinal waves and the transverse waves. So let's see the characteristics of the wave motion. The wave is produced by a periodic disturbance at the point in the medium. So of course the wave is produced only by the periodic disturbances in the point in the medium. And secondly, due to the propagation of the waves in the medium, the particles of medium vibrate about their mean position. So here you can see they are vibrating about their mean position and causing compression and rarefaction. Here they are vibrating about the mean position like this. So that's why they are going to form the crest and the trough. Crest and the trough. So due to propagation of wave in the medium, the particles of the medium vibrate above their mean position without leaving their positions, and energy is transferred with a constant speed from one place of the medium to another place. So energy is transferred from one place to another place of the medium due to this particular or by this particular method. Now some terms related to the wave motion. So these are the important definitions which we need to know now. These are very important and we need to learn them properly. The first one is amplitude. When a wave passes through a medium, the maximum displacement of the particle of medium on either side of a mean position is called as the amplitude of the wave. It is denoted by the letter A, and SI unit is in meters. So I'll do one thing, I'll just draw okay, if this is a wave, now the maximum position from here to here, this over here is A, or here from here to the maximum point over here, this is A, where A is amplitude in meters. Okay, so amplitude is the maximum displacement of the wave on either side of the mean position. Now this is the mean position, तो यहाँ से maximum ऊपर, यहाँ से maximum नीचे, that is the amplitude. The maximum displacement of the wave on either side of the mean position is called as the amplitude. SI unit is meters. The second is time period. Time period is this from here to here is complete, one crest and one trough, or from here to here. This is one wave. So time taken by a wave to form one wave is nothing but the time period. So time period is the time taken to form one wave. So the time taken by a particle of medium to complete its one vibration is called as time period of wave. So this one from here to here, जो time लगा, the time taken from here to here is the time period of this particular wave. So it is denoted by letter T. So next thing is T, which is time period, which is measured in seconds. So it is measured, SI unit is seconds. The next is frequency. Now time period was for one wave, But suppose मैं जानना चाहता हूँ that what is the number of waves in 1 second, then that is the frequency of the vibration. So we say that the number of vibration made by the particle of the medium in 1 second, okay, the number of vibration made by the particle of the medium by 1 second is called as the frequency of wave. It is the same as the number of waves passing through a point in 1 second. It is denoted by F. So that is F, which is the frequency, and frequency is measured as 1 upon second, that is nothing but S raised to minus 1, or it is called as Hertz, Hz as Hertz. The frequency F and time period are related as, so now this, because this is time period is nothing but one period का one wave का time, और ये है 1 second में कितने waves, so automatically what is the difference between the two? It is this time period is equals to 1 upon F, or F is equals to 1 upon T. So this is the relationship between time period and frequency. The time period is 1 upon F and frequency is 1 upon T. The frequency of a wave is equal to the frequency of the wave vibration of its source. So frequency is of the wave is dependent on the source of that particular sound. Frequency is always dependent on the source of the sound. अगर source of the sound का वो भी vibration रहेगा, जो भी vibration source of the sound का है वही vibration और वही frequency जो है that will be of the medium of the wave also. It is a characteristics of its source which produces the disturbance. It does not depend on amplitude of vibration or on the nature of medium in which the wave propagates. So the frequency is not related to the amplitude, it is not related to the in which medium it is passing through, whether it is solid, liquid or gas, but it is dependent only on the origin of that particular source of the sound. The source of the sound is the one which determines the frequency of the wave. The fourth thing what we are having is the wavelength. Now wavelength is the distance from here to here, this over here, from distance from here to here, that is the wavelength, that is called as lambda. So lambda is nothing but wave length. Again it is in meters. This is called as lambda. Okay, I'll write it here. This is lambda. Lambda is the Greek letter which is going to represent wavelength. Okay, so the distance traveled by a wave in one time period. Okay, ये time period में जितना distance the wave traveled, the distance traveled by the wave in one time period is called as one time period of vibration of the particle of medium is called as wavelength. It is denoted by the letter lambda. Its SI unit is meters. It depends on the medium in which the wave travels. Yeah, lambda depends upon the medium in which it's traveling. If the medium is denser, then automatically the lambda will be. So in a longitudinal wave, the distance between two consecutive compressions and between two consecutive rarefactions is equal to one wavelength. So from here to here, distance between one rarefaction and between the two compressions or two rarefactions. Okay, अगर यहाँ पे दूसरा एक rarefaction compression आएगा तो वो दोनों compression के बीच में या तो total यहाँ से लेकर यहाँ तक का जो distance है, that is one compression and one rarefaction, the complete batch of one compression, one rarefaction is one wave. That is nothing but the distance traveled. That is nothing but the wavelength of the longitudinal wave. In a longitudinal wave, the distance between two consecutive compressions or between two consecutive rarefactions is equal to one wave, while in a transverse wave, the distance between two consecutive crests or between two consecutive trough is equal to wavelength. So here they are given as the consecutive, यानी अगर समझो यहाँ पे एक compression है और दूसरा compression यहाँ पे है, तो this is the wavelength. Between this and this is the wavelength. Over here, from here to here, two consecutive crests or two consecutive trough. अगर दूसरा एक trough अगर होता, तो वो this is the lambda. Okay. Or else even this is one lambda from one mean position to the next alternate mean position, where that is one crest and one trough is also equal to wavelength, that is lambda. Now we see the wave velocity. So the distance traveled by a wave in 1 second is called as a wave velocity or wave speed. It is the speed with which the energy is transferred from one place to another place by wave motion. So wave is going to travel in a particular time period and a particular distance. Of course, you know over here that wave velocity will be distance upon time or wavelength upon time. So distance traveled by wave in 1 second is the wave velocity or speed. It is speed with which the energy is transferred from one place to another in a waveform. It is not the velocity of the wave motion. It is not the velocity of the individual particle vibrating about its mean position. It is denoted by the letter V, and its SI unit is meter per second. It may be noted that the wave velocity is constant for a given medium. It depends on the elasticity and density of the medium. It changes with the wave when the wave passes from one medium to another medium. So the velocity with which the wave is going to travel is the wave velocity, and that is dependent on the medium through which it is traveling. It is always seen that if it is a denser medium, then it will travel much faster as compared to a rarer medium. So if any material is solid, that's the reason that the wave is going to travel faster in solids, whereas it will be slower in gases. So that's about the wave velocity. Now we have got over here two types of graphs, that is the displacement time graph and the displacement distance graph. And accordingly we'll be having the relationship between the wavelength, velocity and the frequency over here. So let's take that part. So displacement time graph. So if I got this graph, this is the graph what you have got, and if this graph is such that you have plotted a graph between the displacement and the time, so the time being on the x-axis and the displacement being on the y-axis, then we call that particular kind of a wave as the displacement time graph. Whereas if the time x-axis is the displacement distance, so we first see the displacement time graph. So this like this, that this is the displacement. This is our displacement and this is the time. So in this case you have this particular kind of a wave. So in this wave you get the amplitude over here and you get over here as the time period. So the displacement time graph gives you the amplitude and the time period and also the frequency. The other one is if it is a displacement here and there's a distance over here. So this over here is distance. Then the graph what you get over here, in this case you get the amplitude here without any problem. You get the amplitude. The next thing what you get is this particular distance, which is nothing but the wavelength. So this will give you the wavelength, and combinedly we will also get the, with this and this combined, you will get the wave velocity V, which is nothing but V is equals to displacement upon time. So that is the or V is equals to delta T, lambda upon T. So this, you can see that in the figure 8.8 shows the variation of the displacement with the time of the particles of the medium at a given point. When the wave propagates to the medium, it is called as the displacement time graph. In figure 8.8, the amplitude is represented by the letter A and the time period is represented by letter T. Note that each particle of the medium goes through such motion not simultaneously but one after another as the wave moves in the medium. So yeah, as the wave moves in the medium, so it is going to be continuously in motion. Second is displacement distance graph. In figure 8.9 shows the displacement distance graph of the transverse wave at a distance. Here the amplitude of the wave of a particle of the wave is shown in the letter A and the wavelength is shown as lambda. The curve shows the displacement position of the particles of the medium from their mean position at any instance when the wave propagates. So the medium kaise move karega, that is the thing what is going to be shown over here by the graph. It is called as a snapshot of the wave. So this particular thing over here is called as a snapshot of the wave. Now you can see over here that this we got it as lambda. So this also is lambda. This is also lambda. Over here this is the time period. This is also the time period. And we know that speed or velocity is equal to distance upon time. Now over here the velocity is v, the distance traveled is the lambda, and the time period is time taken is t, is the time taken for one oscillation. So accordingly we know, but we know that 1 upon t is equal to f. See, 1 upon t is equal to f. So therefore v will be equal to f into lambda. So we have got two formulas over here, that v into t is equal to lambda or v is equal to f lambda. So this is the two formulas what we are having with the relationship between of the velocity, wave velocity, the frequency, the time period and the wavelength. So we'll let the velocity of the wave be v, time period t, frequency f and wavelength lambda. By the definition of the wave, the wavelength is equal to distance traveled by the wave in one time period. That is, wavelength into time period is v into t, or v into t is equal to lambda. But t is equal to 1 upon f, so v into 1 upon f is equal to lambda, so v is equal to f lambda. Therefore, wave velocity is equal to frequency into wavelength. So this is how the relationship is taking place of the wavelength, wave velocity and the frequency and time period of a particular graph. So now we see some speed of different sounds in a different medium in the next video.